Good morning, class. So I'm here again. I think you must have understood what was done yesterday. I forgot to give you some homework. I'm sure you must be happy for that. So today I will end up with this part of the chapter and it will be easy for you to do the numericals. So I'll give you some numericals as homework today. So today, yesterday we did the turning effect and when the body is pivoted, when the body is free to move, and what happens when it is a rigid body, what happens when it is not a rigid body, then turning effect, moment of force, couple. So we did all this yesterday. So now today, I'll be beginning with the next part of the chapter. So we go to the next slide. So I begin with equilibrium of bodies. According to the definition, when a number of forces acting on a body produce no change in its state of rest or of linear or rotational motion, the body is said to be in equilibrium. Here I have mentioned net force equal to 0, so translational motion, and net moment of force equal to 0, so rotational motion. Now let us understand this. Yesterday we did that if a body is free to move in any direction and force is applied to that body, the body moves in the direction of force. And this was named as linear or translational motion. And the other kind which we did was if the body is fixed at a point and the force is applied to that body, then the body starts rotating about that fixed point, that is about that axis. And this kind of motion was said as rotational motion. Now, in equilibrium, if it is the case when the body is free to move in any direction, that is the translational case, and the net forces acting on the body become 0. In that case, the body will be said that the body is in equilibrium. And the next one, if it is the case of a rotational motion and net moment of force becomes 0, net moment of force becomes 0, then it will be in equilibrium. So in these both the cases, when it is translational motion, net force has to be 0, and when it is rotational motion, net moment of force, that is the torque, has to be 0. Then the body will be in equilibrium. So we go to the next slide for studying that what are the kinds of this equilibrium. Now in this slide, we are going to study kinds of equilibrium. Now there are two kinds of equilibrium as mentioned here. The first one is static equilibrium and the second one is dynamic equilibrium. So we take one by one. Static equilibrium. Now you know there are two states of body. One is state of rest and one is state of motion. You know this. So when the body is in state of rest and equilibrium, such kind of equilibrium is known as static equilibrium. When the body is at rest, it is not moving. So in that case, it is known as static equilibrium. Now here in the example, you can see that there are some books kept on the table. So now you can see the force, that is the weight of the book is towards the earth. and there is a reactionary force, that is a normal force which is acting above. So you can see that these two forces are balancing each other. They are equal and opposite, and so they are balancing each other. Hence, the books are in equilibrium. So this is static equilibrium because the books are not moving. It is at rest, and so it is in equilibrium. The next case, you can see that there are two children sitting on a seesaw and they have equally balanced it. They are not moving, and therefore this is also a case of static equilibrium. So if I have to say, we have to define, so it will be the physical state in which all components of the system are at rest and the net force is equal to 0 throughout the system, and this will be known as static equilibrium. So we go to the next one. Okay, so now you can make out that what will be dynamic equilibrium. When the body will be in the state of motion and the forces acting on that body will be 0, that is the net forces acting on that body will be 0, in that case it will be known as dynamic equilibrium. Now, for example, a car moving on a road. Now, if the car is moving, then how come the forces acting on that body become 0? It will only be the case when acceleration will be 0. That means if the car is moving with a constant velocity. If the car is moving with a constant velocity, acceleration is 0, because what is acceleration? Rate of change in speed? Rate of change of velocity? So, in that case, if it is constant velocity, acceleration will be 0. And if acceleration is 0, F is equal to ma. You have already studied. So, m into 0 is 0. So, force is 0. So, if the body is in motion and it is moving with constant velocity, then it will be in dynamic equilibrium. Now, raindrops. If I take the example of raindrops, they fall from above and they are said to be in dynamic equilibrium. They fall and the weight of the raindrops, as it has weight, it is attracted towards the center of the earth because of gravity, and there is upthrust of air which is against that gravity. So the two forces are equal and opposite and they balance each other. Hence, the raindrops falling are said to be in dynamic equilibrium. I hope you must have understood till here that what is static equilibrium and what is dynamic equilibrium. I have also given you a few examples which you can make out. So we go to the next slide. So here we come to principle of moment of force at equilibrium. Now yesterday we studied about moment of force and we also did clockwise moment and anti-clockwise moment. If you remember, clockwise moment I said will be negative and anti-clockwise moment will always be positive. And if we have to calculate the net, so whatever is more will be subtracted, and you will put what is how to be added. So what is principle of moment of force at equilibrium? Here anti-clockwise moment will be equal to clockwise moment, so that the net moment of force is 0. That is the case of the rotation. What we studied right now, the case of equilibrium, in rotational motion, the moment of force has to be 0 for the body to be in equilibrium. So principle of moment of force at equilibrium, the net moment of force has to be 0. So anti-clockwise moment has to be equal to clockwise moment. So here in the example you can see that there is a girl on left hand side and there is a girl on right hand side. So the left hand side girl is applying force which is anti-clockwise, and the moment will be her weight into the distance from the pivot, and the other girl is applying clockwise, so it will be her weight into. So when these weights will be balanced, the moment of force has to be 0. That means anti-clockwise moment has to be equal to clockwise moment for this to be in equilibrium. So we go to the next slide. So now let's have some numericals based on principle of moments. Now, whenever I say principle of moments, that means the body has to be balanced, the body has to be in equilibrium, and the case of equilibrium is that the clockwise moment should be equal to anti-clockwise moment. Then only the body will be balanced. Okay, so here we have a numerical. Find out that mark on this meter rule where 10 kg should be hanged. So we have two weights here, two bodies here. One is of 5 kg and one is of 10 kg, and we have a meter rule. Most of the questions in your book are of meter rule only. Meter rule is a ruler of 100 centimeters, 0 to 100 centimeters, and in most of the cases, the fulcrum is at center, and it is not necessary that the fulcrum should be in the center only. The body can be fixed anywhere. I mentioned it yesterday also. It is not necessary that the body is pivoted at the center. The body can be pivoted anywhere, in the beginning, in between, at the end, or anywhere. So a meter rule is there. The weight of the ruler will always act from the middle. That we will study later, center of gravity. The weight of the ruler will always act in the middle of the ruler. So the weight will act from the center, whereas the fulcrum can be placed anywhere. So here in the question we have that the fulcrum is placed at 50 centimeter mark. And there is a 5 kg weight which is at 10 centimeters mark, and we have been asked that where should this 10 kg be hanged so that this meter rule is balanced. That means it is in equilibrium. So according to the principle of moments, anti-clockwise moment should be equal to clockwise moment. Now, here we have to see the distance from the fulcrum. So the body is at 10 centimeter mark and fulcrum is at 50 centimeter mark. So distance between 50 and 10, 50 minus 10, it is 40 centimeters. So 5 kg into 40 centimeters. I have divided by 100 because I wanted to change it to meter. Whereas it will be cancelled because both the sides we are dividing by 100. So 5 kg into 40 centimeter by 100. And the other side, if I take that the body is to be hanged from at x centimeters from the fulcrum, so I have taken x. So distance I am taking it as x. So 10 kg into x. So when we divide it, we get 20 centimeters. So the value of x is 20 centimeters, whereas the mark where the body should be hanged will be 50 plus 20. That will be 70 centimeters. Is that okay? So we go to the next numerical. These all are board problems. You have to do such kind of numericals from the book. I'll give you in the homework. So we go to the next slide. Now in this question, this is a question of 2012 board papers. So now in this question, we have a meter ruler and we have to find out the mass of the ruler. You will get many questions like that to find out the mass of the ruler. Now, right now I mentioned in the earlier slide that the weight of the ruler will always act from the center of the ruler. That means the 50 centimeter mark. So here I have mentioned, you can see 0 centimeter, 100 centimeter weight of the ruler, that is W, is acting at 50 centimeters. And you can also see that the fulcrum is not at the center. The fulcrum is at 30 centimeter mark. We have to find out the mass of the ruler. There is a 10 kg weight which is hanging from 0 centimeters. And we have to find out the weight of the ruler so that this is balanced. So now from the fulcrum, we always find out the moment of force from fulcrum. That means from where the body is fixed, from where the body is pivoted. So here you can see 10 kg from the fulcrum. What is the distance? 0 to 30. So that means 30 centimeters. So 10 into 30. And this side we go 50 centimeters. The weight of the ruler will be at 50 centimeters. So distance from 30. So that will be 20. 50 minus 30, that will be 20. 20 into W. So we can find out the weight of the ruler with this. So weight of the ruler is 15 kg. So 10 kg should be placed at 0 centimeter mark so that this is balanced. So weight of the ruler is 15 kg according to this. 15 kg F I have written. Mass and weight difference you understand. If I have to write weight, I will write kgf. If I have to write mass, I will write kg. So we go to the next question. Now this question I have taken. This is from 2017. It is not necessary that the ruler should be of 100 centimeter only. You can take 50 centimeter ruler also. So here it is 50 centimeter ruler. That means half meter ruler. And the question is that we have to find out the weight of this ruler, whereas the fulcrum is placed at 29 centimeters and the other weight is placed at the end at 50 centimeter mark. So you can see 20 GF is hanging from 50 centimeter mark and weight of the ruler will act in the center. I said so center of 50 centimeter ruler will be 25. So W is at 25 centimeter. Now anti-clockwise and clockwise moment 20 into 21. Now from where 21? The fulcrum is at 29 and the weight is hanging at 50. So 50 minus 29 gives 21. So 20 into 21 is equal to weight of the ruler into 4 centimeters. 29 minus 24, the distance between it is 4 centimeters. So weight of the ruler is 105 GF. Must have understood till now that how the moment is calculated when the body is in equilibrium. So we go to the next slide. So now we have center of gravity. I was saying right now that why the weight of the meter rule will be at the mid of the ruler only. So now we will study that. Center of gravity. So according to the definition, the center of gravity of a body is the point about which the algebraic sum of moments of weights of all the particles constituting the body is 0. The entire weight of the body can be considered to act at this point, howsoever the body is placed. No matter what kind it is placed, the sum moment will be 0. So here I have taken an example. You can see the weight you can see is acting from capital G, that is the center of gravity of this body. Now, I consider that this body, this irregular body is made up of particles. Obviously, it is made up of particles. Now, weight of each particle will be acting downwards. Now, there will be a point at which all the moments for these particles will become 0. there will be a point in this body or maybe outside this body. It is possible that the center of gravity is outside the body. So there will be a point where the moment of force for all the particles of which the body is made up of will become zero. And that point will be the center of gravity, and the weight of that body will be acting from that point. So when I had taken a meter rule, it was at 50 centimeter mark because it is equally distributed, and at 50 centimeter mark there will be center of gravity from where the weight of that meter rule will be acting. So we go to the next slide to understand this properly. So in the last two slides, I have given you some examples of center of gravity. There was a man who was standing on a sphere kind of structure where there was a stand on which the man was standing. There was a large bolt, and you could see that as it was through the center of gravity, so he could balance himself and move to either side, left or right. And in the next case, you must have seen this toy. The center of gravity is towards the bottom, and it moves this side or that side according to the center of gravity. So it is not necessary that the center of gravity is within the body. In most of the cases, it is within the body, but it is not necessary that center of gravity is within the body. The only thing is that all the weights will be balanced at that point. This is to be made clear that all the moment of force acting at that point will be zero. Now this picture has few objects, few shapes, and center of gravity has been mentioned, that at what point the center of gravity will be acting. So first case, we have a circular ring, you can see, and center of gravity is in the center. That means in the mid. Then similarly, we have circular disc, center of gravity is in the center. Then we have a triangular lamina. Any triangle, the center of gravity will be a point at which the medians of the triangle will meet. There will be three medians. What is a median? Median is a straight line passing through the vertex to the midpoint of the opposite side of the triangle. So the point at which the three medians will meet will be the point at which the center of gravity will act. Then we have a rectangle. You can also have a cuboid. So where the diagonals will meet, that will be the point of center of gravity. In a parallelogram, again, where the diagonals meet, that point will be center of gravity. In a square, again, in a cube, again, where the diagonals intersect, that point will be center of gravity. In a rod, it will be the midpoint of the length, and in a cylinder, it will be the center of the circle of the cross section of the cylinder, and it will be in the center of the length also of the cylinder. So you can see where is G. There are some more objects, but this you should know, you should remember this. So this is the center of gravity of these objects. Now I'll give you a few numericals as homework in PDF form over here only after I have given you the presentation. You go through the presentation. If you have any problem, please do ask in the comments, and please try to do the numericals on your own. It will really benefit you. If you are able to do the numericals on your own, that means you have understood well. So please try to do the numericals on your own. If you have any problem, please ask me. On the next turn, I'll tell you the answers of all the numericals and then we will move further. Thank you so much. Bye-bye till then.